Hello everyone, I'm Xinru Wang from Purdue University. Today I'm glad to present our work, Watch Out for Updates, Understanding the Effects of Model Explanation Updates in AI-assisted decision-making. These days, AI-driven tools are being increasingly used to help people make decisions in many areas, such as investment choices, toxic online content detection, and medical diagnostic. To help people evaluate the trustworthiness of these decision tools, many explainable AI methods have been created to explain the reasoning processes behind the black box AI models. For example, post-hoc techniques such as SLIME and SHAP have been developed to show the importance of different features to AI models' prediction. On the other hand, in real life, we know that the AI model underlying the decision tool is not always static. It may get updated over time. The updates of a model can come as a result of different reasons, such as additional training data, more advanced algorithms, or regulatory requirements. Updates in the AI model can result in changes in how it explains its recommendations. For instance, recent studies have shown that different learning algorithms can provide very different explanations. Many empirical studies focus on the effects of AI explanations on end users' interactions with a static AI model. While in this study, we want to ask a currently underexplored question. How do end users of the AI-driven decision aid react to changes in explanations as the AI model gets updated? More specifically, we ask the following research questions. First, can end users perceive changes in model explanations after a model update? Next, will changes in model explanations affect end user trusting and satisfaction with the AI model? And last, what are the potential mechanisms underlying these effects? To answer these questions, we conducted two human subject experiments on MTurk for two decision-making domains where end users may or may not have domain knowledge in. For the sake of time, I will only focus on the second experiment about predicting the default risk of loans, where participants have some prior knowledge in. In each task, participants first review the profile of a loan application and make their own prediction about whether the loan applicant will default on the loan. Then, they were presented with the AI model's prediction, along with the explanations, which included the two most important feature value pairs that influence the prediction. Finally, they had to make a final prediction. In the experiment, we asked participants to complete a sequence of tasks with the help of an AI model. The tasks were divided into two phases, and the model was updated between the two phases. All participants used the same AI model and the same AI explanation in phase 1. In phase 2, however, the AI model was updated in different ways for each treatment group, with varying levels of similarity between the updated AI explanation and the old AI explanations. In order to operationalize levels of similarity between the updated AI explanation and the old AI explanations, in phase 1, we wanted participants to establish a mental model of how the AI model makes prediction. We did this by showing the two most important feature value pairs that model used to make predictions. This way, participants' mental model of the AI model's logic comes as if then rules. If x1 is A and x2 is B, then the model will predict Y. On the other hand, in phase 2, we wanted the participants to realize that their mental models of the AI model's logic were broken down. Given a task instance in phase 2, participants tried to use their if-then rules from phase 1 and expected that the model would predict Y because x1 is A and x2 is B, but only to find out that the two feature value pairs it highlighted had changed. In total, we created 3 experimental treatments. Compared to the two most important feature value pairs highlighted by the old AI model in phase 1, the updated explanation in the high similarity treatment were the same. The medium similarity treatment usually had 1 feature value pair in common, while with the low similarity treatment usually had no feature value pair in common. In this experiment, we account for the direction of the AI explanation change. That is, whether the updated AI explanations were more or less in line with human users' prior knowledge about the domain. So we consider two sub-experiments. As an example of the task instances we used in the sub-experiment where the updated explanations become less consistent with the human knowledge. AI explanations in phase 1 were loan amount and credit score, which matched what most people know about predicting loan defaults. In phase 2, participants in low similarity treatment saw the two feature value pairs highlighted changed to state of address and month of earliest credit account, which were largely inconsistent with their prior knowledge. We obtained users' general common knowledge through a separate pilot study. Now let me describe the measurements we use for each research question and highlight some of our results to you. For the first research question, we asked participants to self-report their perceived changes of the AI explanation after phase 2. Our results show that participants were able to notice the changes in the AI model's explanations after it gets updated. For research question 2, we measured participants' trust and satisfaction gain from phase 1 to phase 2. We calculated the objective trust as a fraction of tasks that the participants' final prediction matched the AI model's prediction. We obtained subjective trust from participants' self-reports at the end of each phase. The trust gain is then computed as the phase 2 trust score minus the phase 1 trust score. Similarly, participants' subjective satisfaction gain is computed as the phase 2 self-reported satisfaction score minus the phase 1 self-reported satisfaction score. We find that people's objective tendency to trust AI does not change with the updates in AI explanation, but their subjective trust in satisfaction with the AI model can be influenced by how consistent the new AI explanations are with their prior knowledge. Move on to the third research question. We first came up with some hypotheses on how changes in the AI explanation could impact people's trust and satisfaction. Then we did path analysis to test these hypotheses and explore the potential causal mechanisms. Our first hypothesis is the more change in model explanations introduced by the treatment, the more likely people would be to notice the changes. Next, the more AI explanation changes that the users can detect, the more or less updated explanations match their own domain knowledge, depending on which sub-experiment they participated in. This change in perceived consistency is computed as the phase 2 self-reported score minus the phase 1 self-reported score. Then, when human users perceive a bigger change in the AI explanation, and when the updated explanations are more consistent with their own knowledge, they tend to believe that the AI model is more accurate after the update. Participants' perceived change in the model accuracy is, again, computed as the phase 2 self-reported score minus the phase 1 self-reported score. Last, after the model update, people's trust and satisfaction with the AI model increase when they perceive the AI model to be more accurate and when they perceive the AI explanation to be more consistent with their own knowledge. The results suggest that our general hypothesis is a good fit for the data we collected. For more details, please check out our paper. Taken together, we found that as the AI model gets updated, end users can perceive changes in AI explanations. Changes in AI explanation may impact how users perceive the AI model by influencing their perceptions on the model's accuracy and how consistent the explanations are with their prior knowledge. Our findings provide important implications on developing explainable AI methods that better support human AI decision-making in a fast-evolving AI development and deployment lifecycle. Integrating human expertise into the explanation update processes, as well as helping users understand changes in the explanations after a model update, are both promising areas for further exploration. That's all about our study. Thank you for listening.